We have one more topic to discuss from section 3.6, and that's finding the slope of a curve that's given with a parameterized function. So if you haven't seen them before, I'll show you a parameterized function in the next screen. Remember the chain rule that we learned last week. dy dx can be found by finding dy du and multiplying it by du dx. So notice that we could use a different variable. If I wanted to find dy dt, I could find that with dy dx times dx dt. So this is what happens when we have parameterized curves. X and y, instead of y being a function of x and y are given separately, and each of those is a function of t. So that's what I'm going to see. I'm going to see x as a function of t, and I'm going to see y as a function of t. Still, I want dy dx. If I want to find the slope of the tangent to the graph that's drawn out by these parameterized curves, so now we can take an expression, that equation, dy dt equals dy dx times dx dt, and just divide both sides by dx dt, and I get an expression for dy dx. This is what you need to memorize. This is what's on your paper. I don't need you to worry about parameterized curves, how to write them, how to graph them. Just that if you've been given them, this is how we can find the derivative. So we'll do some examples. So just as an example, this is an example of a parameterized curve. X is given by the function 3 times cosine of t, and the y-coordinate is given by the function 2 times the sine of t. So as t, which usually stands for time, changes, the x and y coordinates change. If you were to graph these to this function, this parameterized curve, it would trace out an ellipse. So can I find the slope to this curve, even though it's not a function, because it doesn't pass the vertical line test? I can still talk about the slope to this curve. So I'm going to do that by finding dx dt. So the derivative of x with respect to time is 3 times the opposite of sine of t, so negative 3 sine t. dy dt is 2 cosine t. And the derivative, the slope of this curve at any x comma y, any time value, is given by 2 cosine of t over negative 3 sine t. That's dy dt divided by dx dt. So this is the example in your book. It's example number 6 on page 151. You can see that if you knew how to graph this parameterized curve, it would draw the one branch of a hyperbola. We've been asked to write the tangent to this curve at the time when t equals pi over 4. And we know that the x-coordinate is given by secant of t, and the y-coordinate is given by tangent of t. So part A, when time equals pi over 4, the x-coordinate, you're going to plug in pi over 4 for t, and we get the square root of 2, 1 over cosine square root of 2. When time is pi over 4, we want to figure out the y value, so we're going to plug t equals pi over 4 into the y function. You get the tangent of pi over 4, which is 1. So I've written in, that's the ordered pair we're going to use when we need an ordered pair to write the tangent to the function. Now I'm going to try to figure out the slope. I can figure out the slope by finding the derivative. I need dy dx. So start by finding dy dt. The derivative of tangent of t with respect to t is secant squared of t. dx dt, the derivative of secant, is secant t tangent t. Now I can use the chain rule, what I wrote, what's at the top of your notes paper. dy dx, the thing I want, the slope, is given by dy dt over dx dt. So I have the secant squared of t over secant t tangent of t. You can see a secant cancels from top and bottom, so that's just secant of t over tangent t. Now I don't just need a formula for the slope, I need the slope at one specific time, and that's when t equals pi over 4. So I'm going to evaluate that derivative dy dx when t equals pi over 4. I get the secant of pi over 4 or the tangent of pi over 4. Radical 2 over 1 just makes radical 2. And now finally I can write the equation for the tangent line. I've got y minus y1 is 1 equal slope was radical 2 times x minus x1. There's your tangent line equation.